This is the second problem which we are going to look at, and this is also you're familiar with. You have looked at this problem before. So we have a cantilever beam here with a triangular load q, and q says a function of x, of course, right? And at the very right end you have a q naught. So that kind of tells you that your q of x is q naught x. So it's a linearly increasing load from 0 to q naught at the right end over here. And here I've taken the liberty to write the same relationships as we has before. So the more number of times you see the relationships, the more it gets into your head, and you kind of remember that what you are looking at over here. Now if you remember that this problem also we had solved using the method of sections before. So if I just have to go to the previous page, this is what we had solved. We had taken a section X, and we derived the quadratic the shear force diagram, which came out as quadratic, and the bending moment diagram, which came out as cubic over here. So here this was our SFD, and this was our BMD, right? So let's go ahead and now use the relationships to see that if we get the same diagram, same shear force diagram, then the bending moment diagrams or not. Okay, so first of all, let's again go ahead and draw the couple of beams which we always typically do to mark the different diagrams. So I'm going to use this beam for the shear force diagram, and I am going to use maybe this beam for the bending moment diagram that is there. So the first one is for my SFT, and the next one is my BM. So let's go ahead with the shear force diagram first. So for the shear force diagram, as you can tell that here we are going to start with the relationships that is there. So we have this first relationship which we looked at over here, that our dv dx in this particular case is minus of, let's just write the general form first, and then we'll write it to the problem specific, is minus of w, which is a function of x. In this case it is minus of q naught x by l, right? So now since this is degree 1, that kind of tells you that your v is going to be, v will be a second degree, right? And you can simply integrate this one as well, and you can maybe write the expression for v. So let's just go ahead and write that. So we'll get our v as negative of q naught x square by 2l, right? So we know that the shear force diagram, since v is quadratic, so the shear force diagram is going to have a quadratic variation from the left end all the way to the right end, because this load is a continuous load from spanning that entire beam that you have over here. Okay, so now at the left end, again going with our intuition, since this is a free end and there is no concentrated load, here the shear force must be 0. So at this particular point your v is 0. So at a, so let's just mark it here. So this is my a and this is my b. So at a, shear force is 0. So va, we can say that equals to 0. And we know that the variation is quadratic, but let me ask you that what is going to be the slope at a? The slope at a, you see dv dx, the slope at a is going to be this value at a over here, because dv dx I can calculate anywhere. Right now at x equals to 0, which is at this particular point over here, it is going to be minus q naught times 0 by l, and which you can see from here as well. So the slope is going to be 0. So here you are going to have a 0 slope, right? Okay, now what is going to be the value of the shear at the point b? How do I find the value of the shear at the point b over here? Same, we can use this relationship which we have. So I'm going to write that as vb minus va is going to be equals to what? Is the negative of the area of the loading diagram between those 2 points. And what is that? It is the negative of the area of the loading diagram. So half times L times Q naught. Now here I know that my VA is 0 over here. So that kind of gives me that my VB is equals to minus Q naught L over 2. So at B, I am going to have a Q naught L over 2 negative. I'm drawing in the lower half, so I'm not marking with the negative sign. So, and what is the variation from A to B? You're right, the variation is quadratic because I've already found this one over here. So this one is means that it is a quadratic variation. So let's just go ahead and draw the quadratic variation, like this over here. So this is quadratic. Now if I come and ask you that what is the slope of this line at B over here, very easy. This is the expression for the slope, and the slope of this line at x equals to L is nothing but equals to Q naught L divided by L, that is Q naught, which is this one over here, right? Because dV dx is simply the load, the negative of the load over here, so it is going to be minus of Q naught. So let's just mark the slope here as well. So as you can see that it is a concave up curve, so your slope is slowly reducing from 0 to negative slope. So here slope equals to 0. Here slope, see, this slope and all is difficult to compute using the method of sections. You have to again take the derivative and so on. Here it's much simpler because you know the relationship already. So slope is equals to minus of Q naught because it's the negative of the load at that particular point over there. Okay, so we are done with the shear force diagram so quickly. We are almost just done with the shear force diagram. So let's go ahead and draw the bending moment diagram. So let me put another divider line over here. Oops, sorry, let me put a divider line. So next I am going to draw the bending moment diagram over here. Now bending moment diagram, again from simple intuition, here it is going to be 0 because this is the free end. So and if I mark the points at A and B over here, so at M at A will be equals to 0. I have to find the M at B. So let's look at these relationships over here. So I know that dm dx equals to V, and in this particular case I have also written the expression for V over here. So that is minus Q naught square by 2L, so which is degree 2 because we saw the shear is a quadratic. So that means that kind of tells you that your M will be cubic, right? Okay, so now M is going to be cubic. Now I have found that my moment at A is 0 because A is a free end over here. So let me maybe go ahead and write that moment at A equals to 0. I'm going to have to find the moment at B. So how do I find that? I have this relationship that the difference in between the moments is the area of the shear force diagram between those 2 points. So I have my MD, MB in this particular case, MB minus MA, right, is the area of the shear force diagram between this point and this one. Now there are 2 ways to do it. As you can see, it's a quadratic line. You can take this area that is there. Maybe let me mark it with green color. This area you can calculate as 1/3 of that rectangle of a circumscribing rectangle, because it's a parabolic thing with a 0 slope over here. Or you can simply integrate and find out. So what is going to be MB minus MA? I have the expression for the V over here. So it is going to be integral of 0 to L, a negative of Q naught x square by 2L. So that will be L cube by 6. So eventually you will get as minus Q naught L square by 6, right? And I know that my MA is 0 over here. So MA goes 0. So this eventually gives you that your MB is minus Q naught L square by 6, right? So at this point I have a 0 moment, and here I have a negative of Q naught L square by 6. So let me go ahead and draw that vertical drop. So this is Q naught L square by 6. Now Here, although the value is 0, what is the slope? Again, go back to the relationships. It is going to tell you. So here the slope at x equals to 0 is equals to the value of the shear at x equals to 0, which is 0. So here again you have a 0 slope. So let's just mark that. So here you have a flat slope over here, and let's draw the shear. Let's draw the bending moment diagram. So it's a cubic line. So this is cubic. And here, what is going to be the slope? Same dm dx. I'm trying to calculate the slope at b will be equal to the v at b, which is equals to q naught L over 2. So here the slope is going to be q naught L over 2 at this particular point, which is the value of the shear at that particular point. Right. So, and also, as you can say that your bending moment is negative and your shear force is also negative over here. So you have to do more number of problems to sort of get this into your DNA, that how the relationships are and how to use those relationships to get the values of the shear force and the bending moment. So let's compare this with what we got previously in the method of section. So you see how fast this was. We did not have to write an equation and so on. It was just using the relations we get it. This was our shear force quadratic q naught L over 2. This was cubic q naught L square over 6. And this is exactly what we have. So you have a quadratic relationship q naught L over 2, q naught L square by 6. Now, in addition to what we had here before, now we could easily also compute these slopes at these different points that is there. So I hope this particular example was clear to you as well. Write down the problem in your notebook, try to do on your own, try to use the relationship and see that if you end up with the the same values here what we got or not.